Yeah. Yeah. Am I audible? We will be starting this session in another 2 minutes. Is the audio okay, Atharva? Thank you, Atharva. Let's start this lecture. We would like to start JVP. All my JVP colleagues and myself would like to start by paying a tribute to Professor Govind Swarup. We lost him a little over 10 days ago, and he is the father of radio astronomy in India. And radio astronomy is especially useful among other fields to study distant worlds and worlds in the past, including planet systems. So let's start. with a tribute to Professor Govind Swarup. We will move on to the topic, which is Are We Alone? It's a little provocative title for the session, and also a little exciting. Uh, when we say are we alone, this particular session concerns itself with intelligent life elsewhere in the universe, and not just life molecules or not just cells, but intelligent civilizations. And we would focus on our galaxy instead of the entire universe first, because the scales are so vast and so large and so big that even if life exists on other in other galaxies, there's no practical way for us to even know about it, let alone travel. It's the scales are that huge. So we would talk about intelligent life possibilities in our galaxy, what life needs. It's a little bit odd topic because it's not just astronomy related. It's not limited to astronomy, but it's also astrophysics, astrochemistry, astrobiology, biology itself, Earth system sciences, which is a new field, which considers planetary systems as a whole, and looks into the feedback loops in planet scale systems, and of course plenty of probability and statistics as well, and maybe some philosophy too. So it's a mixed topic. It touches multiple aspects, and it's hard to find expertise in that topic. And especially, I would not be doing this session from the position of an expert, because I'm not one. I'm just a reader. I'm an enthusiast about this topic, and I would be doing this session uh, from the position of an enthusiast rather than an expert. But I'm also enthusiastic enough to share what I've found out and what I've read. To keep the session less technical as much as possible, I wouldn't be giving out sources or taking names, um, even though a lot of material in this session has come from books, including by Carl Sagan, by John Gribben, uh, online material from university websites, especially on molecules needed for development of life on planets, and how planets evolve, how stars evolve, life cycles of stars, and so on. So, if you're expecting in this session an answer to this question, are we alone? This is the right time to exit, because you're not going to have an answer to this session really. We're going to look at probabilities, and we're going to look at many exciting possibilities, and also how tough or how easy can it be for life to evolve in various circumstances. So let's start. Uh, Briefly, we'll be covering life beyond our home, where to start looking for in the first place, and then what does it take for life to start? What exactly does it take for life to start? What conditions does it need? Uh, is it very common? Is it easily found? And how probable it is? Uh, when we say is it common or is it easily found, we will talk about DNA, RNA, proteins, etc., but also intelligent life. And how big exactly is the step between life and civilization? That's where intelligent life comes into picture. Uh, this beautiful picture, photograph taken by my friend Rajni Ramnathan, sums it up pretty well. It's a lighthouse with a beam of light, kind of focused on the Milky Way arm that you can see in the picture. Uh, so the search area is our galaxy. We'll limit ourselves to our galaxy as we discussed earlier. It's 400 billion stars, perhaps more. We don't know. We think it's 100 billion to 400 billion, but we started with a much smaller number a few decades ago. Then we moved to 100 billion, then probably 200 billion, then 300 billion. Now we are saying about 400 billion. We don't know. There could be more. So potentially 400 billion plus stars over a span of 100,000 uh, 100,000 light years of the main disk, and a halo around it, a spherical halo, which extends to much more than that, 200,000 light years plus diameter sphere, which is the halo around that galaxy, which also has some stars. And a majority of them would be planetary systems. So we don't know. It could be a trillion planets we're talking about right now, with 400 billion stars, and a lot of them having some planets going around them, including gas giants, of course. And when we talk about astronomy, especially these terms become a little meaningless. There's too much of millions and billions and trillions, and as human beings, we don't really understand it on that particular scale. How much exactly is 100,000 million light years, or how far away is the nearest star from our sun relative to the size of the sun? So we know that Alpha Centauri system is about a little over 4 light years away from us. But relative to the size of our solar system, how much is that? So let's take an example. If you take a medicine tablet, a crocin tablet, half a centimeter in diameter, let's assume. If you consider the sun to be a crocin tablet, half a centimeter in diameter, Alpha Centauri would be another crocin tablet about 1.2 kilometers away. The scales are that big. So it's two crocin tablets separated by 1.5 kilometers almost. That's our nearest star. And if you consider our nearest big galaxy, which is Andromeda or Devyani, if you consider the entire Milky Way to be a crocin tablet, Andromeda would be another crocin tablet a few feet away. So it's closer as compared to distance between two stars, but it's still, if you have to cross from one galaxy to our nearest galaxy, it's still about 25 times farther away than the diameter of our own galaxy, which is why we are going to stick to our own galaxy, and we are going to look at different possibilities of life as well as planet in our own galaxy. This could be extended to other galaxies as well, what we will consider. So a little bit about the history of exoplanets. We now know about 4,000 plus exoplanets already. Two-thirds of them are found by Kepler, the telescope which is specifically designed and operational to find exoplanets. The first one was found in 1992. The first sun-like first exoplanet around a sun-like star was found in 1995. And there are different ways to find exoplanets. The first two that you see here are potentially the most common. The first ever exoplanet found in 1992 was around a pulsar, but the most common two methods are Doppler and transits. Doppler was by far the most common method to find exoplanets before Kepler. After Kepler, the actual visual transits have become more common. And Doppler is the second most common method now. Doppler is essentially you have a star and you have a planet going around it. Any planet going around a star has a gravitational impact on the star itself. So when we say the planet goes around the star, it's not technically right. The planet and the star are going around the center of gravity. But the center of gravity is usually inside the star, which is why we say that for all practical purposes, the planet is going around the star. But it is causing a little wobble in the star itself because the center of gravity is not at the center of the star, it's somewhere outside, just outside the center of the star. So the star wobbles a little bit, and it's a very faint wobble, but you can find it out by Doppler effect. Basically, the star is moving relative to us at a certain speed, and the planet going around it will have a little impact on that speed. It will reduce the speed if it's coming towards us, or if it will increase the speed if it's going away from us because of the planet, basically. So that wobble will show in the Doppler. The radio signals which are coming from the star to us, visual or otherwise, they'll have the frequency, Doppler frequency effect due to the planetary motion. So that's the Doppler way of finding out if a planet is going around that particular star. And then you can calculate with computer simulations as well as complex mathematics, if it's single planet or if it's a system, what exactly is the effect, what is the period of revolution of the planet around that particular star, what could be the potential mass of the planet, what could be the potential size of the planet, and so on. Transit is a little bit of a luck based or lucky break system. So if a planet in its orbit around a distant star comes in front of the star when looking from our perspective, if it comes between us and the star, the light of that star dims slightly. It's like a transit. We see transits for Venus and Mercury, for example, because those are inner planets towards the sun when looking from the Earth. Similarly, there is very minute dip in the brightness and intensity of the star's light coming to us when a planet comes in front. And that's what is caught by telescopes, including Kepler, especially Kepler. And that's how a planet is found out. It's kind of a indirect sighting of the planet. You don't see the planet because it's in dark. You see the dark side of the planet, and you don't really see it. The star is so far away that you just see the intensity dip a little bit. But it's as direct a viewing of any exoplanet as you can get, except a very few which have been actually photographed. The other two are pulsars and effects on disks in orbit. So for young stars, the planets have not all formed. So you have a protoplanetary disk, and you may have some planets which clear some area in the protoplanetary disks, not unlike Saturn's moon clearing some parts of Saturn's rings, basically. So that's essentially how exoplanets are found, and we have found 4,000 plus so far, and many of them are hot Jupiters. Because of the limitation of the techniques that we have, we mostly find planets which are very close to the parent star or which are very big, because big planets will have bigger Doppler effect or bigger transit signature. But it could be a few billion Earths at least. So if you consider the number of stars and number of planetary systems which we have found, and how diverse is the star population around which we have found planets, it could very easily be a few billion Earths. When I say Earths, it's rocky planets, essentially, not necessarily Earth-like, but comparable in size to Earth and rocky planets. So these terms, we call them Jupiters and Earths. Jupiters are gas giants, Earths are rocky planets. And most of the planets that we have found are hot Jupiters, which means they're of the size of Jupiters, but they're very close to the parent star. Many are closer than Earth is to Sun, in fact. So the two gentlemen that you see in the photographs below got last year's Nobel. They were the ones who confirmed the first exoplanets found around a Sun-like main sequence star. They're Michael Mayer and Didier Queloz, and they got the Nobel last year for their discovery in 1995. All right, planet formation. The image that you see on the right is captured by ALMA, Atacama Large Millimeter Array. It's a European Southern Observatory Telescope in Chile, and that's a very famous image because it's of a star which is called HL Tauri, and it's a very young star, and it has a protoplanetary disk around it. And you'll see the gaps in the image. You'll see gaps in the disk itself, and those gaps are potentially formed because of some body there clearing the debris there, clearing the dust and the gases there, which means it's quite possible that those are created by new planets forming. And it's a very young star, of course. and most young stars seem to have those protoplanetary disks. So if you compare the data from Orion Nebula, uh, about 150 stars with protoplanetary disks have been, or planet systems have been discovered within Orion Nebula, which is like a nursery of new stars. Orion Nebula is the closest such area to us, uh, uh, which sees a lot of new star formation, and very young stars, a few tens or few hundreds of million years old, not more than 100 million year old, in fact. 60% of those are seen with those protoplanetary disks, 60%, which is a big number. And older stars, only 9% are seen with disks of such materials around them, uh, which is a good uh, evidence in a way to think that you only see 9% of older stars having those disks because they have now planets around them instead of disks, because 60% of the younger stars had disks around them. And these protoplanetary disks are essentially 98% gas and 2% dust. That's the common distribution. And planets are formed from that gas and dust, essentially. Moving on. So how do planets form? So we'll first see how common it is, how do they form, where do they start, and then we'll move on to how to look for signatures of life, and whether to how to figure out whether it's sufficient to assume intelligent civilization or not. And we'll have to go by our own experience, because we don't know any other species in the galaxy apart from ourselves, any other planet which has life apart from ourselves. So we'll have to go by our own experience, which is a limitation in itself, but knowing it as a limitation and then moving on cautiously with conclusions is a good way. So about 73% of the universe and the galaxy is hydrogen, 25% is helium. All the hydrogen was formed in Big Bang. Almost all helium was also formed in Big Bang. And then the next common elements are oxygen, which is 0.73%, carbon, which is 0.29%. And then depending on whether you count mass or whether you count number of atoms, it's either iron or nitrogen. Iron by mass and nitrogen by number of atoms. And you'll notice that these are all, except helium, which is an inert gas, these are all very active elements. And these are unsurprisingly the most common elements in the universe. And these are also the most common elements in our own system, in our life and on our planet. So you have these most active elements. So how do molecules form? Hydrogen and oxygen combine. Oxygen is a very reactive gas, and it combines with almost anything to form oxides. And hydrogen and oxygen combine to form water molecules. And water, will see the importance of water, but one thing about water molecule is that it has a faint or weak polarity, and which is very critical. It's a specialty of water molecule. So if you see how the hydrogen ions are connected to the oxygen ion with the covalent bonds, the angle means that the electrons are a little bit closer to O compared to H. And so you have a little magnetic positivity on one end of a water molecule and a slight negativity on the other side, which means that it attracts other material, and it encourages other elements to combine with it and form bigger molecules. Or it also encourages water molecules to come together and stick together. It's the same slight magnetic polarity which you see in a water molecule, which causes surface tension on water. And surface tension means water tends to stick together like dewdrops, and it tends to form bigger and bigger droplets of water, and with other material also coming in, the size of that particular particle starts growing. It's no more microscopic, it becomes slightly bigger. And then you have molecules forming with multiple atoms. We have found molecules with 10 plus atoms in space, in interstellar space and circumstellar space as well. So then you have dust grains because you get silicates then and you get carbon. So you get carbides or you get carbon atoms by themselves, and the time for gravity to kick in. So once it reaches a particular size, gravity also starts playing a role, and that's how the molecules build up and then particles build up. Going back a little bit, why in the first place are we looking for something like us and something like our place? Why are we looking for a place like the Earth or like the Sun? Firstly, the lifespan needed. We'll come to that towards the end of this session. The lifespan needed for intelligent life to evolve is significant, and there's a reason for that. So we need a few billion years of stable lifespan. Stable, so the parent star needs to be main sequence because it needs to be stable. Hydrogen, oxygen, carbon, nitrogen, the most common elements in that order, and all of them are reactive if you discount helium. So you need hydrogen, oxygen, carbon, nitrogen. Carbon is 10 times more common in the galaxy compared to silicon, which is like carbon because it has 4 electrons in its outermost orbit, but it's nothing like carbon in the possibilities that carbon has. So carbon has this very unique capacity to create chains and even create rings by joining the two ends of the chain with each other, which is why carbon-based, it's okay to assume that any life that we form, any intelligent life that we find would be a carbon-based life, because what else is there? Carbon is the third most common reactive element in the universe, and it has this ability to form really long chains of hundreds of carbon atoms and with different attachments to that particular chain. Metals. We need metals for life, for intelligent life. This is an astronomer's definition of metals. This is not metals, but anything bigger than helium is called a metal in astronomical terms. So metallicity of a star is basically how much of oxygen, carbon, nitrogen, and heavier elements are there in the star. So we need metals for intelligent life. We need the planet to have some kind of shield, so its atmosphere as well as magnetic field to be protected from solar radiations or any other harmful radiations out there in the space. Stability, the star needs to be stable. This connects to the lifespan needed again. Active feedback system, will come to this later. This is the newer science of Earth system sciences. We'll come back to that. And water we just discussed. Water molecule has polarity, and water is a solvent. Most things can dissolve in water as compared to any other fluid. Ammonia comes close, but it's not that. It's still not as prolific as water in terms of its ability as a solvent. And water has another specialty, which is solid water floats on liquid water. You don't see that elsewhere. Solid of any material sinks because the atoms arrange close to the molecules, arrange themselves close to each other more tightly, and it's denser. In case of water, the crystalline structure of the ice means that there's more space actually in ice. So ice is lighter than water, and ice floats, and which means that it, even in cold conditions, it insulates water by itself, and the chances of having liquid water are significantly more as compared to other solvents. So this is the reason why we are looking for something like us. So when we discuss in this session also intelligent life, we are going to talk about what is it that we have, what is it that makes us special, and what do we need. not just in terms of the basic building blocks of life, but mainly the conditions surrounding which will encourage those building blocks to form more complex organisms and not just a few cells uh, combining together in a very smaller or simpler organisms. So, two things. If at a molecular level, if you want to ask which are the two most important types of molecules that we need for life, DNA and RNA, and proteins, right? And these are basically long carbon-based compounds, which also have nitrogen, oxygen, and hydrogen. So these molecules formation in space because of water mainly. The process follows Majru. मैं अकेला ही चला था जानिब मंजिल मगर लोग साथ आते गए और कारवा बनता गया. So the molecules attach to each other, atoms attach to each other, and you get those long molecules. Now, if you see DNA and RNA, the common building block for DNA and RNA is ribose. Ribose is a sugar with 5 carbon atoms basically. So it's C5H10O5, I think. And that's a common factor between DNA and RNA. In fact, the word DNA and RNA comes from deoxyribonucleic acid and ribonucleic acid. And ribose is the sugar which is common in both. And glycolaldehyde is a 2-carbon sugar, which can easily combine with a 3-carbon sugar to form ribose in any chemistry lab. And we have found glycolaldehyde in space, in interstellar space as well as in circumstellar space. So we have found building blocks of building blocks. So we haven't found ribose yet, but we have found glycolaldehyde, which is and we have found it pretty easily. It's confirmed. It's in large scale and it's found in interstellar dust as well as around stars, in clouds or nebulae around stars. And when you talk about proteins, it's even better. So the building blocks of proteins are amino acids. There are just a few types of amino acids, a few dozen, I think, which form a vast number of proteins. So different combinations of amino acids form that chain, and proteins could be of 1,000 types, but just 20 amino acids can give you those 1,000 proteins by combining in different ways and attaching different kind of different things to those chains, to the open carbon bonds in those chains. And we have found glycine in space, and it's confirmed glycine is an amino acid. And so we have found building blocks of building blocks for DNA and RNA, and we have found building blocks for proteins directly. So we have found an amino acid in space, and we have of course found building blocks of glycine before that, and that was confirmed even before we ever found glycine. So we have basically established that planets are common. We have found 4,000 plus. Almost 60% of young stars seem to have the protoplanetary disk around them, which means many of them, a lot of them, will have planets around them also. We have also found, so there'll potentially be twice or thrice as many planets in the galaxy as there are stars potentially. And we have found out that the building blocks for the basic life molecules, DNA, RNA, and proteins, are also seen and confirmed in space, in interstellar space as well. Which means we don't have to start from scratch for life. You don't have to start from a hydrogen atom and an oxygen atom combining together and forming water. You have to start from glycolaldehyde and glycine, which is similar to starting in a chemistry lab instead of starting completely from scratch. And so chances of DNA, RNA, or proteins being synthesized in space in protected enough environments are there. So we have planets, plenty of them. We have life molecules confirmed. So where are the aliens? And this question is what is called Fermi paradox. It said that Fermi spoke these exact words, but where's everybody? At a lunch table in his university, and some people present there told this story later, and it became legendary. But where's everybody? Basically, what he means is, if they're there, why aren't they here? So if they're present somewhere, and if there are alien civilizations which are probably more advanced than us, they would have had more time to evolve. So why aren't they here? Let's take an example of Carl Sagan's conjecture in his book uh, Dragons of the Eden. He talks about a dinosaur which is named Steno which is about 1.5 meters, so 4.5 feet long, biped. So two front legs, which it doesn't use for walking. Um Binocular vision, so both eyes in the front. 3 digits, 3 fingers basically, which are used for grasping, so which are partly opposable, and which has the highest brain to body mass ratio among dinosaurs and comparable to modern birds. So the brain to body mass ratio, as well as the cerebrum to skull volume ratio, is closer to the modern birds. Uh, Too bad that it got killed in the asteroid strike 65 million years back. But imagine that animal. Carl Sagan talks about this. Imagine that animal. Imagine no meteor strike, and that an animal had 65 million years extra to evolve. Would it form a human-like intelligent civilization? We don't know, but possible. So if there are many such planets and stars which have got the time advantage over us, why aren't they here? Not just why aren't they here, but why aren't they anywhere? Why do we see no signature of an alien civilization anywhere in our galaxy? At least, and agreed that we don't have enough technology to see those signatures, but we should see something, right? So why aren't they here? For that purpose, a lot of initiatives were taken starting from the previous century. This is a little bit of a indulgent slide for me. Carl Sagan's contribution to popularizing science and bringing science into mainstream is significant. But he also brought search for extraterrestrial intelligence into mainstream, and he used his influence to drive the Pioneer and Voyager programs, and the record, the disk which was sent to outer space. This is it, and it has some information printed on it, as well as sounds of Earth on the record. And you also have SETI, SETI, which is Search for Extraterrestrial Intelligence. Incidentally, it was called SETI with a C when it began. So it was CETI, which was communication with extraterrestrial intelligence, and they even sent some radio signals out with that objective, to find alien civilizations. But then probably they got a little scared. So it stopped after that. So sending radio signals out for that purpose stopped. They probably got worried that it will invite unwelcome attention. I don't know, but that could have been the reason. But just imagine if there are 1,000 alien civilizations, all scared to send out radio signals out, and all scared to find each other. Bill Watterson says it the best. Sometimes I think the surest sign that intelligent life exists elsewhere in the universe is that none of it has tried to contact us yet. It's Calvin and Hobbes, always the last word. But when we talk about SETI, we have to talk about a particular equation. It's called the Drake equation. It's basically the equation of probabilities, and Frank Drake formulated that equation. What you see on the screen is the original version of that equation, or the second version. The original version could be what you see on the whiteboard behind Frank Drake. And when you say an equation, you're expecting some guidance, right? Or if not answers, at least a guidance. This equation will not give you any answers at all. It just tells you what factors at the minimum could play a role. So it's not an answer-oriented equation, which is probably why Frank Drake is looking so grumpy in that photograph. But all of these are probabilities, except the first number. Everything else is essentially probabilities. And like principle of probabilities, probability of A plus B happening is probability of A multiplied by probability of B. So let's just consider these terms one by one very quickly. N is the number of intelligent civilizations which could be out there. And N star is the total number of stars in the galaxy. So you have 400 billion plus, which is N star. Fs is the probability of the star being a sun-like star. So let's call it a main sequence star maybe for now. Fp is the fraction of stars having planets. So nearly all, perhaps. Ne is the number of planets, average number of planets around the stars, which are Earth-like, and which also means that they are in the habitable zone of that particular star. So we could say at least 10%, maybe, if that's a conservative estimate, maybe. Fi is the probability or the fraction of those systems which have developed life. And that's a good question. That's anybody's guess. We don't know, to be honest. Fc is the fraction of those life systems which have developed cognizant or intelligent life. That's Fc. And that's again a really good question, but we have no clue. And FL is a little interesting. FL is the fraction of an intelligent civilization which has the technical ability to communicate outside that particular solar system, compared to the total lifetime of that particular planet. So if you've had this ability on Earth for the last 100 years, FL would be 100 divided by 4.5 billion, which is the lifetime of Earth. And the average lifespan of a civilization is a complicated topic, because historically, what is a civilization? Humanity is a civilization, or each individual civilization which developed in ancient China? Probably there were 10 in China. There were at least 2 in India, maybe more. You have Greek, you have Roman. How do you count civilizations, and how do you define civilizations, and what impact will it have on this particular equation? We don't know. So moving forward, we need to take our chances through eliminations, essentially. So what we are talking here is, let's take all the possibilities that we have and let's eliminate. Let's apply the filters based on our own experience. What do we need? And based on observed data as well, not just our experience, but based on what we observe in those 4,000 plus planets which we have found in space. So main sequence star. Why main sequence star? We'll come to that. Single stars, potentially, because binary and especially tertiary systems have a lot of complications. A planet going around a 2-star system can have a lot of perturbations in its orbit, and it may or may not have the stability which is needed to sustain a few billion years of lifetime. Size of the cluster in which that star was formed. Metallicity, which is the metallicity of the star itself in terms of how much of oxygen, nitrogen, carbon, etc. are present in the star and around it, and refractory depletion from the star to the planets. We'll talk about this a little later. First, let's talk about the type of star. We often hear these terms. Sun is an ordinary star, right? Or we even if we try to look for life around a star which is just like the sun, that will still give us a lot of probabilities. But is the sun very common? So saying that sun is an ordinary star and saying that sun is a commonly found star are two different things, right? So when we say ordinary, it has a definition in terms of the classes of temperature and size that the star has. So these are the classes O, B, A, F, G, K, M, and what you call ordinary is essentially F, G, and K. These are the main sequence stars. So sun is bang in the middle. If you see 5,500 to 6,000 Kelvin temperature on the surface, obviously. You have F and K. F just above it in terms of temperature and size, and K just below it. And then you have those other classes. In these classes, 75% of the star population falls under class M. Almost 75%, 70 to 75% population falls under red dwarfs. 5% falls under O, B, and A, broadly speaking. So when you say main sequence, it's basically just 20% of all the stars in the galaxy. Now, why can't we have planets? Why shouldn't we consider planets around the big blue giants or the red dwarfs? Give us long enough. Blue giants, supergiants, and hypergiants have very limited lifetime. So when you say lifetime of a star, it's inversely proportionate to the size of the star. So when you say sun burns hydrogen to create helium, how much of hydrogen does the sun burn? So it's basically the gravity of the sun is pulling it inwards, and the nuclear fusion, the energy created from nuclear fusion, is pushing it outwards, and that's what helps the sun keep its balance. And if you again talk about, let's go back to the kerosene tablet thing, instead of just talking about million tons of tons of hydrogen and millions of tons of helium. If let's assume for a second that all of us in the world are weighing 100 kilos. We are not, hopefully, most of us are not, but let's say all of us weigh 100 kg, 100 kilos. So we are 7 billion of us, right? And all of us weigh 100 kilos. The sun takes in every second, every person in the world, mass of hydrogen equivalent to every single person in the world, assuming everyone weighs 100 kilos, and gives out helium, which in weight equals almost every person in the world except, let's say, Argentina, or except, let's say, Odisha, the state in India. So about 45 million people, 40 to 45 million people. Only those don't come back. So the entire world population goes in as hydrogen, and entire world population minus Odisha comes out as helium. What happens to Odisha? E is equal to mc square. So that gets converted from mass to energy, and you have that much of hydrogen going in every second, and that much of helium coming out every second, and the energy is what we get in the form of light and heat. So that's how the sun works. The bigger the star is, the gravity is much bigger. So sun can go on doing it for about 8 to 10 billion years, because its size is small and relatively its gravity doesn't have to be compensated by too much of burning hydrogen. But bigger stars typically have a few thousand or a few millions, in fact, years of lifetime, not sufficient for evolution and not sufficient for intelligent life. Red dwarfs are very stable, and red dwarfs have the same lifetime, like billions of years of lifetime, just like main sequence stars, but they're very dim and they're small, which means to be in a habitable zone around the star and to get enough light and enough heat for water and other solvents to remain fluid, the planet has to be very close to the red dwarf. And when it is that close, typically the planet has to be 10% of the distance between the Sun and Mercury, that close to a red dwarf for liquid water to exist on that planet. And that will cause the planet to be tidally locked to that particular star. Tidally locked planets are not good places for development of life, unless you can, I mean, you might want to consider the twilight zone, which is always in twilight between the dark side and the bright side. So that's a possibility. But the second thing is that red dwarfs are not as stable as main sequence stars in terms of intensity. So red dwarfs can have spikes of energy output, which could suddenly make them 40% brighter uh, for a short time. And imagine sun becoming 40% brighter even for a short time. That could be really, really dangerous for the planet, not just the life on the planet. So we'll stick ourselves to main sequence stars. Not too clingy, not too unpredictable. So red dwarfs are too clingy because they cause tidal locking, and they're also too unpredictable. If you consider single stars only for now, a third of all main sequence stars are single stars, which means a majority of main sequence stars are binary or bigger systems. Uh, Size of the cluster. Now, we know that when the solar system was formed, it formed from a gas cloud, which was which was not the which was not made from stars from the first few generations, because there needs to be sufficient oxygen, nitrogen, carbon, and heavier metals up to iron, and even heavier metals than that present, which means there have to be multiple generations of stars before we get the cloud from which the sun is born. And secondly, to trigger that process of uh, collapse of the cloud, and to seed different elements into especially the radioactive elements in that cloud, you potentially need a supernova explosion, not close enough to disperse the cloud, but close enough to collapse the cloud, to help the cloud collapse. And you don't want too many supernova explosions also, because once the solar system is formed, and if you get a supernova explosion 2 light years away, that's going to be the death for the solar system, and especially life. So it needs to be just the right size to have the right number of potential supernova explosions, and also the right number of close companions. So in bigger clusters, what happens is stars are more closely packed with each other. So if another star passes even, let's say, 1.5 light years away from a solar system like ours, it's going to have a significant gravitational pull on the outer planets like Uranus, Neptune, etc. So you don't want stars to go too close from potential life planets. Uh, sun is a good example. The closest star to us is 4 light years away, which is a safe distance. So to have that kind of packing of stars, and to have the right number of supernova explosions to trigger the gravitational collapse of the cloud, as well as seeding of the cloud with heavy elements, you need the cluster size to be approximately 1500 to 3500. This is John Gribbon's conclusion. Then you have metallicity. This is a little controversial topic. It's called GHZ, or galactic habitable zone, and which derives its concept from metallicity of a star. So if you consider sun's metallicity, and count the metallicity of stars uh, relative to Sun. And if you see the 4,000 plus planets which we have found out so far, uh, all of those planets go around stars which are at least 40% as metallic as the Sun, at least. Some are more metallic than the Sun, but very few. But there is no single star around which we have found a planet yet which has metallicity which is less than 40% that of the Sun. Uh, that's because solid rocky planets need either carbon or silicon. Obviously needs oxygen to combine with carbon or silicon to form those solids. It could be silicon carbide, it could be silicates of different metals, it could be silicon oxides of silicon, etc. Or it could be liquids such as methane, or it could be CO2 and CO in gaseous form. You need metallicity. And older stars, very old stars, which are older than the Sun, older than 10 billion, older than 5 billion years. There are stars in our galaxy which are older than the galaxy itself, which means the galaxy acquired them from eating other galaxies in early days. Older stars are not metallic because remember, we started at the Big Bang with hydrogen and helium only. That's it. So the first few generations of stars didn't have much metallicity at all. It's only the later generations of stars which are having more metallicity. So you have the halo around the galaxies pretty much eliminated because they are very old stars. You have the bulge, the galactic bulge also is full of old stars, but it still has a lot of stars which are higher in metallicity. But the problem with the bulge is that the stars are too close to each other. There are two problems with the bulge. The stars are very tightly packed, and it's difficult to imagine planets going around one star which cannot be perturbed by any other star system. That's uh, pretty unlikely. So you can, for safety, it's possible that there could be planets around those stars which are in stable orbit for a few billion years, but the likelihood is less. And the second thing is that the black hole at the center of the galaxy, the supermassive black hole, because of that, there's a lot of activity and a lot of very strong radiation in the bulge of the galaxy. So that radiation as well as the periodic activity or the occasional activity, which is quite unpredictable, because the black hole can swallow a nearby star and give out jets of radiation and matter create from the accretion disk. All of that is not healthy for a stable solar system. And so you've cut out the halo, you've cut out the bulge, so you have a zone in the disk of the galaxy which is kind of in the middle. So that's 10% of the stars in the galaxy. But it's a controversial topic because it doesn't necessarily eliminate everything in the galaxy. That part of the galaxy, which is essentially the spiral arms, not the bar, not the bulge, but the spiral arms, have a much higher number of stars with the right metallicity. That's what it means. It doesn't mean that there aren't stars with sufficient metallicity in any other part of the galaxy at all. It's just that the likelihood is significantly low. The next important factor is refractories depletion from the star to the planets. So this is very interesting. Refractories are materials which remain solid at high temperatures. So you have calcium, aluminum, for example. Those are the metals who have their boiling point is much higher, and you need those for rocky planets. Our sun, as well as all the stars which we have observed to have planets around them, you see a significant depletion of refractories on the surface and in the atmospheres of the stars. So you can figure out what is on the surface of the star or in the atmosphere of the star using a technique called as spectroscopy. Each element has its own unique signature. Each molecule also has its own signature, which is dependent on the signature of the elements in it. And the science to find that out is called spectroscopy. So you can find out how much of refractories there are in the atmosphere of a star. And you see significant depletion around the star and on the surface of the star, which has rocky planets around it. You don't see the depletion around on the surface of stars, which only has gas giants around it. Why the depletion? Anyone's guess is that the reason behind the depletion is that all the refractories have gone in creating the rocky planets, because rocky planets will need aluminium, calcium, silicon. So the refractories are depleted on the star because they have been taken by the planets forming around it during the early days. So we don't know if that's a causality or if that's just a correlation. Maybe that's not even correlation. This is based on our sun and the 4,000 plus planets which we have seen. It's possible that it's not even a correlation, but for now we see that we see a relation between depleted refractories and rocky planets, presence of rocky planets around the stars. So that basically reduces the number of stars that we should target significantly. If you see, so only main sequence, only a third of the stars, metallicity, size of the cluster, and refractories. Even if you don't count metallicity as a factor, and if you don't consider 10%, let's consider 20%. Let's consider some stars from the bulge also. But if you see the fraction is growing smaller and smaller. So that's about the sun. That's about the stars and the sun. What about the Earth's family? What about the solar system? What about we talked about the blast wave created potentially from a supernova or potentially from the solar system passing through a galactic arm just at the right time to cause that compression and collapse of the cloud. Just give me a second. Yeah. So we will just run through the remaining presentation in the interest of time. But so we have seen the blast wave at the seeding. So that's special. Another special thing about our solar system is the orbits are nearly circular for Earth, especially Venus as well. Mercury is quite elliptical. It's about 1.5 times as compared between the furthest and the nearest point to the sun. Mars is also elliptical but fairly circular. Most of the gas giants, a lot of the gas giants which we have found as exoplanets do not have exactly circular orbits. Orbits are primarily elliptical. The same goes for super Earths as well. You need to have water and carbon present in exactly the right quantity. In our solar system, the computer simulations suggest that gas giants formed, Jupiter formed a little farther away from where it is today. And then it's called Grand Tack. Jupiter came in, young Jupiter, before any of the rocky planets were formed. Young Jupiter came in due to the gravitation of the sun. Saturn formed behind it. Saturn and Jupiter at a point had a 1:2 tidal locking, gravitational resonance, and Uranus and Neptune formed. They pulled Jupiter back a little bit, and Jupiter went back to where it is right now. But in this process, it cleared the debris in the inner solar system. It didn't allow a planet to form between Mars and itself. It didn't allow Mars to grow bigger. This is all coming from computer simulation, starting from different initial positions and the current position of our solar system. So we can call it Jupiter Dada's blessing. So it's not just that Jupiter stops a lot of comets coming into the solar system today, but its grand tack, the term comes from sailboats. Its grand tack going against the solar wind essentially helped uh, define the snow line. It just went out of the snow line at the end, but you see a lot of dust inside in the inner solar system and the gases outside. So that's movement of dust versus gases, and a snow line which is defined, which is just inside, uh, just between the orbits of Mars and Jupiter, beyond which water cannot remain in liquid state. So it's always in ice form. So we'll just move further. Home. So this is a little interesting. So we just spent a couple of minutes on this. I hope you've all heard the story of Goldilocks. Goldilocks is a little girl, and she enters the house occupied by three bears, and the three bears have three porridge bowls. The three bears have three beds, three chairs, and Goldilocks tastes porridge from one bowl, and oh, it's too hot. In the other bowl, too cold. And then the third one, oh, this is just right. Same thing happens when she tries sleeping into the bed. So she goes to the Papa Bear's bed, and oh, it's too hard. And she goes to the Mama Bear's bed. Oh, it's too soft. And then she goes to the Baby Bear's bed. Oh, this is just right. So that just right concept uh, gives this name to the habitable zone around a star. It's called Goldilocks zone. The name comes from the fairy tale of Goldilocks. Earth is in the Goldilocks zone and like almost bang in the middle of the Goldilocks zone. If you consider the strictest definition of Goldilocks zone, it starts from about 95% of Earth's orbit and goes to about 110% of Earth's orbit. So Earth is right in the middle. There are other definitions of Goldilocks zone which are much broader, but they make assumptions such as so Mars could be in the Goldilocks zone by that definition if you assume Mars had sufficient atmosphere, but it doesn't, so it's not in the Goldilocks zone. Formation of moon. Earth is the only planet which has a significantly bigger moon, relatively speaking, and is the only planet amongst the inner rocky planets which has a proper moon. So Mars has two rocks going around it, which we call its moons. I don't think they are even round. I'll need to check. But so Earth has a big moon, which has the crust rocks very similar in nature to Earth's crust rocks, and it has very tiny core, and Earth has a pretty big core, and Earth has a two-layered core, a solid core inside a liquid floating core. And the best explanation of this, again, this is a hypothesis, but this is the best explanation so far of how come we have such a big moon, which seems to be so similar in the material, especially on the crust, to us, but very different in the core. So during the very early stages of planet formation, there was several dozen candidate planets inside Jupiter, 20 to 30 planets, and there were a lot of impacts, planets coming together, planets destroying each other by crashing into each other, etc. And we ended up with 5 planets. So we had Mercury, Venus, a young Earth of the same size as Venus, Mars outside, and there's a 4th planet, which is called Theia. It's a hypothesized planet, but that's the best explanation of Moon and the best explanation of Earth's core, which formed potentially, as the computer simulation suggests, at one of the 2 Lagrangian points in Earth's orbit around the Sun. But the problem is when it grew too big, it couldn't be sustained there because on Lagrange points, the objects oscillate. Let's not get into the details of how Lagrangian points work, but essentially it crashed into Earth. So Theia crashed into Earth. Why is it called Theia, by the way? Thea was in Greek mythology mother of Selene. Selene is the moon goddess in Greek mythology, and Thea was Selene's mother, which is why the planet is named Thea. If you want to find an Indian name for Indian mythology name for Thea, it would be Anusuya, because Anusuya was the mother of Chandra in Indian mythology. So this Thea, or you can call it Anusuya if you want, crashed into Earth. Their cores combined, and a large amount of debris was thrown out. It was a violent uh, uh, impact. Uh, a large amount of debris was thrown out. That debris basically converged together to form the moon, and the debris uh, was mainly the mantle and the crust. The core combined, Thea and Earth's cores combined, which is why Earth has supersized core. And speciality of Earth's core is that it's in two steps, and it's a rotating solid core in the center, in liquid iron core around it, which essentially is the reason why we have a strong magnetic field, and which is why we are protected from a lot of harmful solar radiation, in spite of being just 8 minutes away from the sun. And that also explains why the rocks in the moon's crust are similar to Earth. It also explains why the moon has a large mantle and a thick crust, but very, very small core. And we also had exactly the right amount sprayed on us due to the grand attack of Jupiter and due to the asteroid belt around it. So if you see the asteroid belt, 20% of it is water, 20% of it is frozen water, whereas on Earth, we didn't start out with any water at all, because we were a molten planet. And even today, the amount of water on Earth is just 1%. It's just the right amount. Too much of water, too much of debris inside, which was full of water vapor, essentially ice turned into water vapor, would have bombarded us with more water, and we could have just had a water-filled planet with thousands of feet deep ocean and no land at all, no water, and we wouldn't have had life. We have exactly the right amount of water. About 1% of our mass is H2O, and that's thanks to the Jupiter's grand attack, that we were sprayed with water, but just enough water. Right, and the last thing is oxygen needs to beat carbon. So oxygen and carbon are kind of balanced in the universe and in the galaxy. You will always see any star that scientists study. It is dominated by carbon or oxygen. Both are reactive. Both are similar, third and fourth after hydrogen and helium in their presence in the universe, and very reactive. So you have one, they combine to form CO and CO2, and you have one which remains. So oxygen needs to beat carbon to have an Earth-like planet, because then you can have silicates. For rocky planets, you need to have silicates. For thin crust and volcanic activity and tectonic activity, you need to have silicates. If carbon beats oxygen, you'll see all the oxygen gone in carbonates and carbon dioxide and carbon monoxide, and you will have a graphite crust and potentially a diamond mantle, because it will be dominated by carbon instead of by silicon and oxygen. Right? So for Earth-like planet, you need to have oxygen beating carbon, and you either see one of the other in all stars that you see, one of the two. And oxygen is needed though, because a carbon based rocky planet with graphite crust and diamond mantle doesn't have any feedback, can't do anything. Even the oceans will be of tar, because oceans will be of like methane and other hydrocarbons instead of water. So we need oxygen to have that feedback loop, which is what Earth system science is all about. And if you see the lifespan very quickly, the horizontal bar that you see is the planetary scale of Earth, which is 4.6 billion years. You have the first fossil evidence of life, which was prokaryotic, which is basically non-nucleus life, at around 1 to 1.2 billion years afterwards, 3.6 billion years ago. Then 2.4 billion years ago, you have little more complex eukaryotic life, which is cells with nucleus and other components, cell wall, cytoplasm, and uh, the energy cycle of the cell. Then you have one event in Earth's life where uh, the life on Earth exploded. It's called Cambrian explosion. It's at the period was called Cambrian. It's at the beginning of the Cambrian period. Everything before that is called Precambrian, and nothing much happened before that except we got a few very simple multicellular organisms and mostly unicellular organisms. So we have the Cambrian explosion at this point, which is just 700 million years back, which triggered a lot of diversity on Earth. All the modern phyla that you see start at that point, and you saw dinosaurs emerging, and then you see dinosaurs getting finished uh, by the asteroid hit 65 million years back. So 700 to 65 was when life really bloomed on Earth and continues to bloom today. Even though we lost all the dinosaurs and a lot of other species during the asteroid hit. This is, by the way, that Stenonychosaurus animal, which is, in terms of brain size, the most advanced dinosaur. It developed right at the end of that period and got killed, unfortunately, or else we wouldn't be having this session now. This is we are entering the final few minutes of the session now. So this brings us to a field of study called Earth System Science. Again, I have not studied this. I've just read about this on material which is publicly available on the internet, including on NASA Science Mission Directorate. This basically considers planet scale systems as a whole, and it considers the feedback loops, it considers the carbon cycle, the water cycle, the climate variability, and how important it is to have that feedback loop and to have the cycles of so when there is greenhouse effect, you have some feedback mechanisms which stop that greenhouse effect from happening naturally, and the other way around. When you have ice ages or when you have snowball Earths, what causes more CO2 to be released into the atmosphere so that greenhouse effects start and the planet warms up a little bit. So this is pretty close to a controversial hypothesis called Gaia hypothesis, which was conceptualized by James Lovelock a few decades back. And it was just unfortunate. The naming was unfortunate, but you see a lot of overlap between Earth system science now, which is considered proper science, and Gaia hypothesis. There's a lot of overlap, but Gaia hypothesis met with a lot of criticism because it called itself Gaia hypothesis. Gaia is the Earth goddess in ancient Greek mythology. So sometimes we rush in deciding what's science and what's pseudoscience. So James Lovelock was not really a welcome person around that time. If you see now, NASA has no problem taking his name in Earth system science. That's how things work. But James Lovelock had looked at Mars in 1960s and said that don't send anything there. There is no life on Mars. We can tell from here because by studying the atmosphere, you can tell whether it's a feedback friendly system or not. And Mars is 96% CO2, 2% argon. There isn't enough there to have any kind of mechanism for sustaining and growing of life. So no point in sending probes there in search of life. Just study the atmospheres of planets, and that will tell you if the planet is because of the system of feedback. That and now we see that there is a merit in that way of thinking, that the feedback loops and the cyclic natures of carbon, climate, and water are important. So So what you see essentially is while the life molecules, the building blocks of DNA, RNA, and proteins follow Majrooh, intelligence life follows Gulzar's lines more. So मैं अकेला ही चला था जाने पे मंजिल मगर लोग साथ आते गए और कारवा बनता गया is true for molecules, but there's so many filters and so many elimination rounds that uh, uh, planets hosting intelligent civilizations will face this particular line more often. ऐसे उजड़े आशियाने तिनके उड़ गए बस्तियों तक आते आते रस्ते मुड़ गए. So a lot of civilizations till reaching the point where they can become civilizations, raste mud gaye. This is because of a series of coincidences which we have seen on the earth. We still don't know, and this is not saying that there isn't another intelligent civilization in the entire galaxy, but this is just basically tempering our view. So we oscillated between two extremes over the last couple of thousand years. We went from humanity was created by God in His own image, so that kind of special, to the Copernican humility or the Copernican mediocrity that, oh, we are just an ordinary rock around a very ordinary star in one arbitrary arm around the galaxy. There would be thousands and thousands of civilizations which are way ahead of us, and we aren't being contacted by them because we are not important enough. So from those two extremes, we just want to acknowledge the coincidences which are needed for a planet like Earth to form and a carbon-based life to evolve into such a complex civilization in terms of molecules as well as in terms of history, that it is not impossible that we are the only one in the galaxy. It's in the realms of possibility. There could be a few other civilizations we don't know, but it's very unlikely that there will be thousands. And it is also possible that we are the only one in Milky Way. Possible. So that possibility is what I was trying to bring out in this particular session. And so a little bit, last 2 minutes, Atharva, a little bit. This is a science session. This is not a social or political session, but everything comes down to policy and science, and especially scientific policy. So this image was taken by Apollo 8, and this image kind of gave a lot of encouragement to the climate movement. This image told humanity for the first time how a thin wafer of an atmosphere protects us from just being another dead rock in trillions of dead rocks around in the galaxy. And it's important that we handle it carefully, and it's important that we not just acknowledge the feedback loops, but we protect them. And apart from the natural organic feedback loops for carbon and oxygen cycling and weather and climate, there is a man-made activity in the last couple of 100 years, and that's important. So we need to be aware. We don't need to be scared, and we need to take actions on that. And it's not as simple as just taking a cloth bag to buy grocery instead of a plastic bag. In my opinion, plastic is not a problem. Waste management is a problem. It's okay to use plastic bags if we do waste management properly as a country. There are bigger problems, and it needs some lifestyle changes. I'm sorry. So if you're in India, there's no way you can wash your cars with a hose pipe. We simply don't have enough water, for example. Or if you still want it, there are ways. So if I can afford a 700,000 car, I can afford a 3,000 rupees high pressure hose pipe, which will consume very little water but create a lot of pressure. Or if I can afford a home in Pune, I can afford a couple of thousand in installing two flushes in my toilet, a small flush for number one, a bigger flush for number two. And these are the lifestyle changes which we should look for, not just taking a cloth bag for grocery instead of a plastic bag. That's me preaching. That's not the objective of the lecture, but it coming back to the Earth system science kind of triggered this. So I would just like to leave you with these final lines from Gulzar. uh, बस चंद करोड़ों सालों में सूरज की आग बुझेगी जब और राख उड़ेगी सूरज से. दिस इज प्रीटी साइंटिफिकली एक्यूरेट बाय द वे. जब कोई चांद न डूबेगा और कोई जमीन न उभरेगी, तब ठंडा बुझा एक कोयला सा टुकड़ा ये जमीन का घूमेगा भटका भटका. मैं सोचता हूँ उस वक्त अगर कागज पे लिखी एक नज्म कहीं उड़ते उड़ते सूरज में गिरे तो सूरज फिर से जलने लगे. So I would like to leave you with those beautiful words to end this session. If you have any questions on this session, this is my email ID. I'll just flash this momentarily and go back to the previous slide. And about JVP, you can access us on jvp.org.in. JVP mail IDs are there. We are on Twitter, WhatsApp, Instagram, and you can also download JVP app from Apple and Android Play stores. Thank you very much. We'll take questions now for a few minutes from the YouTube audience as well as anyone here. So I'll just leave this slide for a minute and then go back to the previous one.
Thank you, Yogesh, for nice lecture. So we'll just take a couple of questions maybe.
Yeah.
So first question is, could you please explain the great filter concept?
Right. So this is basically all the filters that we saw at the star level, then at the solar system level, and then at the planet level. So what were crucial factors or essential factors for us to exist on Earth? We needed a main sequence star. We needed the right metallicity. We needed the right refractory depletion for rocky planets. We needed oxygen to beat carbon in solar system. We needed a gas giant protecting us by clearing some of the debris in the inner solar system, but then not staying here, instead going back. So we needed the other gas giants to pull it back too. We needed a big core. We needed a rotating core inside liquid core to have the magnetic field. Otherwise, we would end up like Mars without much magnetic field and without much atmosphere. We needed water. We needed to be in the Goldilocks zone. We needed a moon to basically control our rotation. So we rotated too fast when we were hit by Theia, or even when we were formed. And the moon basically controls the length of our day. And in fact, it's slowing down the length of our day by a tiny bit as it's moving away. So we needed all of that. Without any of that, without a single factor in that long list happening, we wouldn't have ended up where we are. So this is the list of filters which we have jumped through. And it's possible that any intelligent life for existing will have to jump through at least similar number of filters, if not exactly the same filters. That's the concept. That's the viewpoint. Does it answer your question?
Yeah. Okay. Thank you. The next question is regarding the recent discovery of phosphine gas on the clouds, in the clouds on the Venus. So, what do you think about the life on Venus with respect to that?
Yeah. Again, I don't know. I'm not an expert, but it was an exciting news. It was found very high in the Venusian atmosphere and phosphine, and it was found in amounts which can't be explained by what we know as the processes. In gas giants, you find it needs a huge amount of energy to create phosphine, which is not available on Venus. So we can't explain that. That doesn't mean that automatically it was created by bacteria the way it is on Earth, but that's a possibility for sure. And the surface of Venus is definitely ruled out for any life. It's 400 degrees Celsius. Life can't really exist there, but in the upper reaches of the atmosphere, temperatures being lower, and it's possible for water vapor to stay there in form of water globules or water droplets. It's not impossible that unicellular organisms live there inside those water droplets, and they're responsible for phosphine. But it's a conjecture at this point of time, and we'll have to wait for the scientists to come back with more data on that. It's exciting for sure, but we have found glycolaldehyde and glycine in space, right? So this is as exciting as that, probably, perhaps not more. I'm cautious.
Yeah, thanks. One last question. So, how Kepler detected planets?
Kepler uses transit basically. So Kepler, being outside the Earth's atmosphere, just like any space-based telescopes, its capacity for seeing things is much more enhanced and accentuated. So when a planet goes in front of the star, when looking from our side, this needs the lucky factor that the orbit of the planet needs to be aligned with our line of sight. And when the planet comes in front of that star, the light of that star dims by a tiny fraction of its normal output. And that gives us a blip, and the period of that blip tells us how much time the planet spent in front of that particular star, and how big the planet was in terms of size. And then further observations can be done from ground-based facilities to check the Doppler shift of that particular star and figure out if we can find the mass of that planet and whether it's a gas giant or a rocky planet, and so on. But after Kepler, there's a sudden spike in the number of planets that we found. So since 2012 onwards, the number of planets that we found is significantly higher. So that number was, I think, 600 before 2011, and now it's 4,000 plus. So between 1995 and 2011, we found a few hundred. Now we have in thousands, and that's thanks to Kepler.
Okay, so we'll stop here for today. Thank you very much, Yogesh, for the wonderful lecture, and thank you everyone for joining with us today, online, of course, on YouTube, and we'll announce our next lecture in this series very soon. So please stay connected. Thank you very much. Have a good day.
Thank you. Thank you, everyone.